Hello everyone, my name is Ahmed Rakfat, a cloud engineer at Cloud Softway. We'll talk in this session about DevSecOps pipelines. What's the importance of security in the development lifecycle? How can we improve security and how do we make it an essential part of our CI/CD pipelines? We need to check after every stage the security of the previous stage. We shouldn't postpone security until after we've finished the application or released it, only then starting its security checks. In this presentation, we're going to review several points. First, what are the issues with the traditional approach to security? After that, what is the importance of DevSecOps? We'll also talk about the pipeline. So, what is the correct DevSecOps pipeline? We start by checking for secrets first, then we proceed through the code itself, through the dependencies and the container image, and then through the live application. Finally, we'll discuss the importance of the reports generated by the DevSecOps pipeline and the business value it provides us.
Okay, we have a number of points to discuss in the...
Let's discuss the security issues we face with the traditional approach. The primary concern is that the more delayed a security check is conducted, the significantly more challenging and complex its subsequent remediation becomes. This also makes it considerably more costly, potentially leading to critical system downtime, and an attacker could easily exploit these weaknesses to achieve higher unauthorized privileges on our system. The more we delay the security or check process, the more problems we'll face. That's why we recommend checking the security after each stage. And then after that, we look at the... after that, the second issue we encounter in security problems is manual reviews. During manual reviews, if a human is performing a code review, they might, for instance, overlook a specific pattern. They could also miss vulnerabilities present in a particular library and not realize that there's an underlying problem. Furthermore, certain secrets might go unnoticed by them. Secondly, thirdly, retention. If, for example, an API key or an AWS password, an AWS key or an AWS password is found within the Git history, we might not be able to fully check the complete history of our Git repository. Also, as we've discussed, the dependencies that are present within the libraries. But there could be a specific library or a particular dependency that has a problem. So we might not have a fully updated view that this library has an issue. Therefore, we need tools that are constantly updated and integrated with automation to help us find the problem proactively. Okay, what is DevSecOps? DevSecOps means we integrate security after every stage in our fully automated CI/CD pipeline without reducing delivery or delaying releases. So before we even start reviewing the code, we first check if there are any secrets. Then we proceed to review the code itself. We also review all the dependencies. We begin to look for any potential issues within the container image, or even after we've deployed this image, we can perform a live track checker. If we encounter any problems, we are able to immediately halt this image. So we've implemented a shift left for security, moving towards a fully automated process without any manual intervention. Manual help. And also continuous feedback. We're improving the feedback process. So the pull requests themselves, the pull requests will contain the issues we found so that we can accelerate the feedback with developers. Cloud Softway's Monorepo actually contains 3 distinct applications. All 3 of these applications inherently possess security vulnerabilities. So we deliberately chose to utilize these existing security vulnerabilities within the code in these specific environments to thoroughly test the code. This was done to fully comprehend the nature of the results generated by these tools. We have there were 3 distinct projects residing within the Monorepo. The very first project was Python using the Django framework. Then the second application was developed in PHP, and the third application was ReactJS. Well, the truth is there are common tools that we can use across all programming languages, and then there are specialized tools for a specific programming language, like, for example, Pyodide, which checks Python's dependencies, or NPM audits, which checks the dependencies or packages for ReactJS. There are also other common tools, like, for instance, Derivi or...
This was in all the workflows or all pipelines.
Okay, our pipeline, or an overview of the pipeline. First, we check for secrets. We use two tools for this, Git leaks and Trapero. After that, we perform static. We check the code itself, a code review. We check the code itself. We analyze it using semgrep and CodeQL. SST stands for Static Application Security Testing. Then we check dependencies, which is software composition analysis. We perform software composition analysis for the existing dependencies using Snake, PyUp, and NPM audit. Initially, we start by checking if there's a problem within a specific library or a particular package. After that, we then check the container itself. We check the image inside the container using the Rave, and subsequently, we check through the. After that, we conduct dynamic testing. Specifically, we carry out dynamic application security testing through OAZ. We check the live application as it's running so that if we encounter any problem during its operation, we can resolve it immediately. All of these reports are then made available on GitHub. We have established a service to ensure they are uploaded automatically to GitHub Security, where we can easily access them. Reports usually contain HTML output and TXT files, making them easily human readable, and there's also a comprehensive summary mark that effectively gathers all of the data into a single convenient location. And finally, at the very end, there is an artifact or an archive available, so that if all of these reports are downloaded, they will be readily accessible to us in one centralized place. Alright, our first stage is dedicated to secret scanning. For this secret scanning process, we actually utilize two distinct tools. The primary tool, the first one, is named Git Leaks. Now, this particular tool is designed to meticulously check for over 150 different patterns of sensitive secrets. These include, for example, an AWS secret key, a database password, a GitHub token, an API token, or any similar credential. It checks against these particular patterns, and it also provides support for certain predefined rules. We can even add additional rules ourselves should we wish to do so. We also check the full Git history and the working tree. We have a tool called Trafog. It's similar to Git leaks, but it has more patterns. It validates for secrets and can do so via a real API call. So we use these two tools to ensure our repo contains no secrets, whether in the working directory or in the Git history in general. All right. Next, I will discuss static application security testing, or SAST, specifically using semgrep. This particular tool scans the actual code itself without needing to run the application, which makes it incredibly fast within CI and perfectly suited for the continuous integration process found in CI/CD. It's also capable of detecting many very common security issues, such as SQL injection, cross-site scripting, command injection, and various others. Well, semgrep, it actually detects these kinds of issues, pause, by essentially building an abstracted syntax tree, pause, for the entire code base, and then it extracts, pause, those problems using predefined security rules. Pause, it then generates its output through a serve output that we can we upload it, and it will be available on GitHub Security, and remediation guidance is also provided if we want to solve these problems. The second thing that we have available to us within SAST is CodeQL. This particular tool is actually provided by GitHub. It's considerably more in-depth, you see. semgrep, for instance, performs a kind of pattern matching with our code. If it detects a pattern match, then we have a security issue right there. It's very fast, but CodeQL offers deep analysis, semantic analysis, and the data flow tracking across multiple functions and files. This is very important for complex vulnerabilities like SQL injection or XSS, because it tracks the problem, and the problem might be present in more than one layer of the application. That's why we use CodeQL. We also use it with Python, JavaScript, or ReactJS. It checks with every push and every pull request, and then uploads its security report to GitHub Security. The third stage that we have with us is some dependencies vulnerability scanning. This allows us to check for any potential issues that might be present within a library or a package. Pause. We can find them because the vast majority of the libraries that are used in our code are from third parties. Pause. And because of that, they might contain CVEs or specific vulnerability issues. So we should, for example, in Python, we are utilizing safety and also employing Pepit audit. This is specifically to check, for instance, the requirements.txt file. And for ReactJS, we are using npm audit as well to thoroughly verify all the packages that are currently present within our ReactJS codebase. Okay, so for the fourth stage, it's container security through Dravi. Yeah, we've already finished scanning. We finished sorting. Okay, so we've completed the inspection. We're done checking all of the dependencies, and we've also thoroughly examined the code itself. Next, we're going to start checking the file system, and then we'll proceed to check the image itself. We have two primary uses for Dravi here. The first one is a Dravi file system scan. This scans source files, and it also checks any dependency manifests right before the Docker build. It helps us identify problems before we even start the image build process. The second type is the image scan. This examines the Docker image itself layer by layer. We might find ourselves discovering problems, for example, within the operating system package, or perhaps a base image that isn't quite secure enough. This could be because we're using, for instance, an older base image, or one that's simply not appropriate for our project's specific requirements, or a base image that might potentially contain vulnerabilities, leading to a significant security vulnerability issue. So then we can immediately detect problems through the Dravi image scan. Additionally, if there are any secrets present in any layer of our application, we are able to locate them. And if there's an application runtime CVE, for example, a specific library that's not functioning, we can find it while the application is actively running. And then at that point, as our focus is on its outputs, which are produced as critical, high, and medium, and we might then, for instance, be able to accept a medium issue, but we absolutely must address the critical and high ones. The fifth stage is OWASP. We have important static analysis, yes, but then we really need to look at the application itself while it's actually running. So we will begin with dynamic application security testing. We have two types, or rather two layers, OWASP baseline and OD OWASP active full scan. This particular stage deals with the application as it's running, exactly like a real attacker or a hacker would, trying to find any potential vulnerabilities within our application. This process is fully automated. Now we build the image, then we run the container on an isolated Docker network. We then make sure the application is running and reachable. But after that, we start with the initial basic scan, and then we perform a full active scan. The reports are generated in HTML format so that they are human readable, and their appearance is very easy for anyone to understand what problems are present. And this gives us a clear vision of the issues. And we also use it to check for the top 10 vulnerabilities that are commonly tested. Things like OWASP failures, the OWASP top 10 failures, broken access control, cryptographic failures, or various types of injections such as SQL injection or XSS.
All right, team. I think it's about time we got started with our attempt on the OWASP.
We have two OWASP items to discuss. The first one is the OWASP baseline, which is specifically the baseline scan. This is a passive tool that performs checks on the application. When it detects traffic, it identifies relatively simple issues, such as missing headers or insecure cookies, and also information disclosure, without actually sending any real attack payloads. This makes it extremely well suited to be run very frequently within the CI pipeline. But later on, we will need to conduct a much deeper and more secure test. So we utilize an OWASP full active scan because it performs more extensive crawling and thoroughly checks for additional rules. We can also define further rules and provide a username and password, allowing it to attempt to create a genuine user. And it transmits a specialized payload specifically engineered for comprehensive testing to thoroughly examine for vulnerabilities such as SQL injection or cross-site scripting XSS, or other critical flaws like broken authentication mechanisms and various other impactful security concerns. This scenario offers the most accurate depiction of a genuine attacker's operational workflow within the continuous integration and deployment pipeline. One of the most significant strengths inherent in the DevSecOps pipeline is its ability to provide unified reporting. All the tools we utilize generate alerts, which we then store within an artifact and subsequently upload. This allows us to download this artifact and thoroughly understand all the alerts that have been generated, or indeed all security issues.
and there's like a centralized security system available on GitHub.
Besides that, we also save HTML reports or TXT files, all this data from every single post. And we also use Markdown to gather a summary of all these reports in one place, measure costs, so that we have a centralized view and can immediately understand that multiple tools are flagging issues. And we also have an artifact archive where we store all the reports that are generated from the DevSecOps pipeline. The business value isn't solely technical, it also significantly enhances our delivery or our release process, effectively reduces potential risks, and provides a comprehensive audit trail. And it generally helps to significantly reduce the overall level of risks involved. It also greatly enhances and streamlines the entire development process. Additionally, it effectively minimizes the cost associated with any necessary fixes. We're sort of past that point where we don't need to wait for a live application to have a problem and then go fix it, causing us downtime. No, from the very beginning, we know that if an issue arises after a specific stage, we simply resolve it and then proceed with our release. It also significantly reduces human interaction with the system and consequently human error. This means we no longer need a human individual to constantly monitor and oversee potential problems. No, instead we now have a completely and fully automated pipeline in place. It also improves the feedback mechanism through pull requests, helping developers to continuously refine their skills and get better over time. Why is that important? This is because we have, immediate feedback right away. If we encounter an issue after a particular stage, we can immediately revert to the developer, informing them of the problem in that specific area so they can resolve it. We don't wait for them to release a full product and then tell them, no, there are security issues 1, 2, 3 that we need to solve. This improves the developer, also from a security perspective, because he knows when every issue occurred and how to quickly resolve it. Right? Additionally, this pipeline also supports governance and compliance requirements. For ISO, it provides clear evidence of secure development practices, and for SOCO, it facilitates the detection of code incidents through automated scanning and alerting. As for GDPR, it actually supports privacy by design, specifically through the use of hard-coded circuits, and also the ongoing process of reviewing both the TDCs and the container. And also through OWASP, it is fully compliant with OWASP standards because it provides both SAST and DAST capabilities, all integrated, directly through the OWASP guidelines. This allows us to effectively check for the OWASP top 10 security vulnerabilities, and we also perform a comprehensive code quality analysis for our entire code base. Here, we're also observing how this particular pipeline is, in fact, very much connected to secure code. This is not merely just a theoretical concept or an abstract idea. No, we have actually implemented it, and there are certain controls in place. This is achieved by our ability to perform secret detection. Through this, we significantly reduce any potential secret leaks. Furthermore, we enhance the quality of the code, for instance, using SAST, and we have successfully integrated security directly into the development pipeline, specifically within the CI/CD process. GitHub Actions is fully automated. It also supports security-driven operations and ensures efficient delivery. And it also provides comprehensive visibility and detailed reporting so that we have clear reports available, allowing us to fully understand them and effectively resolve any problems.
So security is like integrated into the system, not something just added at the very end.
So in our next step, we are going to evaluate our security controls through a very clear and well-defined life cycle, and we'll be implementing automated testing and policy enforcement. Additionally, we are going to significantly improve the overall visibility of our application. This will be accomplished through a centralized system for monitoring and comprehensive reporting. Furthermore, we are aiming to greatly enhance team awareness regarding security, as well as improve our security development practices. We are actively fostering a stronger culture of support and understanding among our team and developers concerning security. And it's also crucial to continuously review and optimize our application and our entire DevSecOps pipeline. Ultimately, these modern DevSecOps pipelines are constructed using cloud-native software for organizations that increasingly require a highly scalable, automated, and auditable approach rather than relying on haphazard or purely manual solutions. It helps teams to move faster, reach releases more quickly, and significantly improve the entire development process. It also elevates the level of both security and governance. First of all, thank you all very much. We're now going to start showing the results from the DevSecOps pipeline on Python code. All right, for the DevSecOps pipelines that are available on our Cloud Software repository, we actually have 3 different projects, one in PHP, one in Python, and one in React.js. We'll mainly be explaining the Python one as our primary example. We also have the various workflows that are currently in use. We have 5 distinct workflows. One, of course, Python has its own dedicated workflow. Users are employing all of these as essential security tools. PHP developers are utilizing these specific tools, and React.js developers are also making use of these particular tools. Now, regarding Python for CodeQL, we've implemented CodeQL, which is directly sourced from GitHub. And for React.js, we are also using GitHub CodeQL. They've outlined for every single stage which specific tool they've utilized for scanning. For SAST, they're using SemGrep. For software composition analysis, they're using SIFT, Web Audit, and Trivy. One for the file system and another for image scanning in case of an issue with TBC or the base image. For secrets, they're using GitLeaks and Trayfin Hub. For DAST, we use OWASP Zap Baseline and OWASP Zap Full Active Scan. And the reports that are generated for us, each one is produced in its own specific format, and we've also established a centralized repo or a summary where all the results from the various checks are stored and maintained in summary.md. If we want to, for example, look at the actions, we want to see the action specifically for Python, for instance. For example, this repository here contains all the nuggets. For instance, SIFT identified 93 vulnerabilities. We know the repository we're using is a bit old, so there are definitely vulnerabilities in the libraries and components present. Similarly, Audit also reported findings of around 108 vulnerabilities. He found 34 TBCs. If we open up the requirements.txt file right here, we'll actually find that there are indeed 34 TBCs listed within this file. For OWASP Zap, we'll take a look at the result together, God willing, in a much clearer way. But it also managed to produce these particular results. And regarding SemGrep, it also reported several errors, meaning quite a few high priority issues. And it contains warnings with 21 identified as critical. And then there are 112 more as a medium issue. These are also the results that came out from Travi. The same situation applies to GitLeaks, which didn't find any secret or any finding as a secret present in the repository or its history. If you want to download, you download the artifact that contains all these files. It comes down to us as a zip file. This is after, once we've accessed the zip file, it contains all the files. We'll begin, for instance, by using GitLeaks to find secrets. And these are all the patterns that it attempts to search for within the repository. It attempts to locate, for example, any password, any key, or any existing token. For instance, I consider an AWS access token here. There's a particular pattern that was run, and it didn't find anything at all. So in the very end, the results clearly show that it didn't locate any of these items. Therefore, our repository, based on this specific pattern, contains absolutely no secrets. All right, let's move on to our second point. We'll begin, for example, with the audit where we check the TBCs of the Python packages that are listed in the Python requirements file. Here, we'll open it up. Okay, here, for instance, it found quite a few things that need to be updated or require us to use a more recent version. For example, let's consider cryptography. Here, the existing version is 39. Well, to update or fix this particular version, the best approach is to use the most recent one that came out, which is 46.0.5. If we open something like SIFT, for example, it's another thing that also checks on TBCs. Oh, it's Saif. She's right over here. Perhaps the format here is a bit different. But for instance, like if we developed something in cryptography, was there an issue or anything? Here, for example, it told us that this image indeed has a problem and it's better to upgrade and use a new version. It found that version 39.01 has an issue and it's best for us to upgrade. If we get a link like related to SEM, if we search for it, we'll actually discover that this specific version of the GraphGraph library has a significant problem, and it would definitely be better for us to perform an upgrade. Then we'll need to go back to reviewing our outputs. After that, for example, we'll proceed to look at semgrep. Semgrep here is indicating that it has thoroughly scanned almost all of these particular files, essentially every single file that's located within the repository. And these are the number of rules it tries to check. As we previously discussed regarding semgrep, semgrep contains specific patterns that it looks for to see if they are present within the code. Because if they are, this could potentially lead, for instance, to vulnerabilities like SQL injection, or perhaps XSS injection, or even code injection. So it attempts to match these specific patterns. It applied these rules and patterns across all the files that are located here. And ultimately, of course, every single output indicates whether there might be an error or anything of that nature. And finally, it also clearly shows how it actually performed the scan. Here, for example, it scanned 500 rules. I've examined more than 99% of the lines present in the repository. Its outputs, for instance, indicated 133 findings, and then we'll start to analyze the findings that it discovered. Later, regarding Trevi image scan, just you can check the scans that was done on the image itself. Its output usually comes in the form of something like tables. Here it specifically checks the existing base image that is of the Debian type. What I mean is it checks the image itself. If we want to start looking specifically for critical issues that are returned, here, for instance, I'm encountering two rather critical issues within this particular base image. And if we were to search further, for example, for any other potential problems or concerns, here, for example, another critical issue has come up for us. So we'll have to look for all the criticals and the high priority ones. And then we'll see if, for instance, the accepted one is ours, which is just for medium issues. Here, for example, it also provides us with a useful link. If we were to copy this link,
And we search for information about it.
here we will find the name of the CVE, the ID for the CVE ideal integral overflow. This has its criticality, its description, and its weakness. And this problem was present in any stored version and occurs in any int version.
So regarding the OWASP ZEB, we have, as we've already discussed, two distinct testers. The very first test is what we call the symbol baseline test. And for this baseline, the output that we receive is always generated in an HTML format.
Well, you'll have the high, the medium, and the low. It's simply, as we've already discussed, just checking if there's, for example, a missing endpoint or perhaps a missing header or even cookies or anything else of that nature.
So here he was able to identify 4 medium issues. For example, the number of instances, the endpoints, or the locations where he found this exact same problem. If it's systematic, then it's definitely present within our security system. For instance, here we have a missing configuration and also a missing header. If we were to click on the problem, for instance, it would provide us with a description of this particular issue, and it would also tell us where the problematic endpoints are located. So these are all the endpoints that have issues, and this is a description of the problem. Now, regarding the always full active scan, it also outputs in HTML format. Here, it managed to identify a high severity one. OWASP truly behaves like a real attacker on our application. We also added rules. Yeah, for example, we defined username and passwords. Signing, someone might enter pretending to be a user, try to sign in and sign out, and check the database for any vulnerabilities. It could also show us, for example, SQL injection, remote executions, code injection. Here, for instance, he managed to identify one high severity vulnerability, but it was present across 2 distinct endpoints. He also managed to find 8 medium severity issues. Up to this point, we'll see the same vulnerabilities that were already identified in the baseline. However, we will also be adding new findings that he discovered through his comprehensive testing process.
Should we click right here on the problem, it will then present to us exactly what the issue is, along with its full description.
Here he was able to access the actual server
issue, which was Unicorn. He realized it wasn't there, indicating a proxy disclosure vulnerability. These are the endpoints he used to identify the problems. First, sign up and password reset. We'll find the same issues in the medium as well. So at that point, we'll just have to try and solve all these problems. And he's going to keep repeating this test every single time we manage to fix one. And then we run the workflow. He'll perform the exact same test. And the full active scan test is the most time-consuming test. The more time and rules we add, the better the results we'll get. All right, we've concluded our session on DevSecOps pipelines and their benefits, the business value of DevSecOps, and how we'll increase security in CI/CD pipelines.
If there are any questions or anything else you'd like to know, please feel free to ask us, and we'll be happy to answer, God willing.